When a laser beam traveling through the air strikes a dense, curved block of glass, it snaps into a new trajectory. To understand how optical instruments work, we have to start by isolating that first interaction, a single spherical interface separating two media with different refractive indices. A refractive index is simply a value measuring how much a specific material slows down and bends light. This diagram maps the mechanics of that bending. Light travels from an object at distance u in the first medium, n1. It hits the spherical boundary with a radius of curvature, r, and refracts into the second medium, n2, heading toward an image point at distance v. The severity of the light's redirection is dictated by the radius of curvature. A steeper curve forces a more drastic change in direction, while a flatter surface bends the light less. This interaction is defined by a single equation linking the object distance, the image distance, the refractive indices, and the curve of the glass. This equation perfectly describes light entering a medium, but practical optics, cameras, telescopes, the human eye, rely on light passing completely through a medium. We need to build a bounded system. We transition from a semi-infinite block of glass to a functional tool by adding a second boundary. This animation shows the construction of a double convex lens. It is simply two distinct spherical surfaces, each with its own radius of curvature, placed back to back. Light traveling through this lens must obey the laws of refraction twice, once when entering the first boundary and again when exiting the second. The engineering challenge is mapping this entire two-step process using a single mathematical formula, relying only on the physical properties of the lens itself. To derive that formula, we break the system apart. We treat the two surfaces as a sequential chain of events, where the output of the first interface becomes the exact input for the second. We begin by isolating the front surface of the lens at pole B, completely ignoring the existence of the back surface. Light from object O strikes the first curve and converges. If the glass extended incidentally, these rays would meet at point I1, the intermediate image. We quantify this step using our single surface formula, tying the object and image distances to the first radius of curvature. The exact position of that intermediate image is the solitary output of this first physical interaction. Even though the light will never actually reach that point in physical space, locating it mathematically is required to solve the rest of the system. Now, we reintroduce the second surface of the lens at pole D. This boundary intercepts the light rays before they ever reach point I1. For this second boundary, the incoming light is already bent. It carries the trajectory given to it by the first surface. Aiming for the intermediate image, the light treats it as a virtual object. Striking the final glass-to-air boundary, it bends again, converging to form the true physical image at point I. We map this exit back into the air using the second radius of curvature. By defining the non-existent intermediate image as our virtual object, we link two independent boundaries into a continuous logical chain. We have two equations, but they conflict. The first measures distances from the front pole of the lens, and the second measures from the back pole. To merge them, we apply the thin lens approximation. This animation demonstrates the concept. A thin lens is defined as one where the physical thickness between the front and back poles is negligible compared to the distances of the object and the image. Compressing the thickness to 0 makes the distance from the front pole to the intermediate image mathematically identical to the back pole's distance. We no longer have to measure from the front or the back. We can measure from a single optical center. By sacrificing the physical reality of the lens's actual thickness, we entirely eliminate the coordinate mismatch that was blocking our calculation. Here are the equations for both surfaces. We add them algebraically. Notice the terms mapping the intermediate image distance. Because these distances are identical under the thin lens approximation, but with opposite signs, they cancel out completely. The consolidated formula depends solely on the position of the original object, the position of the final image, and the physical shape of the lens. The virtual middle step is entirely erased. We are left with a direct mathematical relationship between the light's entry point and its final destination. To determine the inherent focusing power of the lens independent of where an object is placed, we evaluate the system at an extreme, placing the object at infinity. This shows light from an infinite distance arriving as perfectly parallel rays. As seen in this diagram, the point where these parallel rays converge is defined as the principal focus. The distance from the optical center to this point is the focal length, denoted by f. By setting the object distance to infinity, the left side of our combined equation simplifies down to precisely 1 over f. We now have a clean metric for the lens's permanent focal power. This equation is the finalized lens maker's formula. The first term, isolating the refractive index, represents the material choice. It is the specific optical density of the glass compared to the air around it. Looking at this 3D model, the second term, the difference between the inverse radii, represents the physical geometry. This dictates exactly how the glass must be ground and polished. This is the operational blueprint used by optical engineers to translate a desired prescription into a tangible physical tool. By reducing a continuous block of glass to a sequence of individual surfaces, the mathematics proves that the total power of any lens is strictly the sum of its boundaries.